Good morning. Hope everybody's doing all right this morning. We are going to finish up section 1.8 today. We had gotten to example 4 and got to start on that one, so we'll finish that up, finish up the rest of these examples. Then after we finish that, we will go through the practice test because I told you that's what we would do today. We should have plenty of time to get through both of those things. I think we'll be good. So we'll do that. Don't forget that you do have the homework on sections 1.5 to 1.8. I did move that due date to tomorrow night at midnight. It was originally due at midnight tonight, but since we're going to finish up 1.8 today, I thought it was fair just to move that back a day. So that means the test will be due by midnight tomorrow night, and that homework assignment will be due by midnight tomorrow night. Okay, but that gives you the rest of the day today and tomorrow to get both of those things done. I think that's all for me in terms of announcements. So any questions, comments, concerns before we start today? All right. If you think of anything, just let me know. And then if you do have questions, before you take your test or anything, please email me. I will be responding to email throughout the afternoon, and I'll be around tomorrow also. So if you've got any questions before you take your test, if you want to take it tomorrow, that's fine. Okay. All right. So if you remember yesterday, we were looking at this problem. We're trying to show that it's continuous on the closed interval from -1 to 1. So the first thing we said we had to do was just show that it's actually defined on that interval first, right? And that's what we did here, was we took what was inside the square root, we set it greater than or equal to 0, because we know we can't have any negatives inside the square root. And that showed us now that the domain for this one is -1 to 1, right? So we know it's defined for all those values from -1 to 1. The next thing we're going to need to show then is that the limit actually exists for all the values in the domain of this function, right? So what I'm going to do here is I'm going to say, let's let some value a be between -1 and 1. So I'm going to say -1. Give me 1 second. My pen's not writing. There we go. So -1 less than a less than 1. Okay, so I'm letting some a value be a real number between -1 and 1 now, because that's where I need to show that this limit exists. And what I'm going to do next is I'm going to take the limit as x approaches a of our function f of x. All right, now the function f of x is the function that's up here, 1 minus square root of 1 minus x squared. So that's what I'm going to take now, is the limit as x approaches a of 1 minus the square root of 1 minus x squared. Now I want to apply all of our limit laws that we know to see if we can break down this limit so we can actually evaluate it. So what's one thing I can do to this limit based off of our limit laws? Okay, good. So we can split up the subtraction here, right? So let's break that up first. I'm going to take the limit as x approaches a of 1 minus the limit as x approaches a of the square root of 1 minus x squared. Okay, so whenever you've got addition and subtraction, remember we can split that into two separate limits. All right, what can we do from there? All right, good. The limit of a constant is the constant, right? So the limit as x approaches a of 1 should just give us 1. All right, can I do anything with that other limit now? So if we have a square root inside of a limit, what are we allowed to do? Okay, so yeah, we can take the limit of the inside and then just apply the square root to the whole thing, right? So remember, we're allowed to bring out that square root. So we're going to take the square root of the limit as x approaches a of 1 minus x squared now. Well, 1 minus x squared is a polynomial. So how can I find that limit now? Okay, so we actually don't have to factor this one, right? Because I'm only looking for the limit as x approaches a. But if we're taking a limit of a polynomial, what are we allowed to do? Substitute, right? So I can just direct substitute that a value everywhere I see an x now. So that's going to give us 1 minus the square root. And in this case, substituting the a value in there is just going to give us 1 minus a squared. So that's what our limit as x approaches a would be equal to, meaning that our limit exists for all values between -1 and 1 now. Now, what does this down here look like? So this, what we got, 1 minus square root of 1 minus a squared, what does that look like now? So look back at your original function. What's the only thing that's different between what we got as the limit and what the original function was? Yeah, there's just an a in there instead of an x, right? So this thing that we got down here now is just the value of the function evaluated at a. Well, what that tells us then is if this limit is equal to f of a, then the limit at all values between -1 and 1 are equal to the value of the function at those points. Therefore, we know now that it's continuous from -1 to 1. Okay, so this tells us now that our function is continuous on the interval from -1 to 1. Because remember, to prove continuity, we have to show first that the function is defined there. We did that. Then we have to show that the limit exists. We did that. And then we need to show that the limit is equal to the value of the function at those points. And that's what we've shown here, because our limit is equal to f of a. That means that all of those values there are going to give us the same value as the limit itself. Any questions up to that point? Okay, now, there's only one other thing we have to show now. We've shown that it's continuous for the open interval from -1 to 1. We still need to show that it's continuous at the endpoints now, okay, which is not very difficult to do, okay, but we still have to show it because remember, at those endpoints, it's only going to be continuous either from the left or from the right, and so that's why we have to do those separate. Okay, so what I'm going to do next is I'm going to look at the limit as x approaches -1. Would I be looking at that limit from the left or from the right? From the right, good, right? Because -1 is the leftmost endpoint, so I can only get values from the right-hand side of that point. So I'm looking at my limit as we approach -1 from the right of f of x now. Now, we could basically show all the same work that we showed over there with our a values, okay? And we could actually do a direct substitution. And so really all we're doing now, if we're taking the limit as x approaches -1 from the right of 1 minus the square root of 1 minus x squared. If we direct substitute in there now, what's that going to give us? It's going to give us 1, right? Because if we substitute the -1 in for x, that's going to give us a -1 squared, which is 1. 1 minus 1 gives us 0 under the square root, and then 1 minus the square root of 0 is just 1. Okay, so we get 1 for that limit. Now, we just need to show that that is actually equal to the value of the function. We basically just did that, right? Because we did a direct substitution to get that limit anyway. So now we can say that this is equal to f of, -1. And so that right there shows that we have continuity from the right at that leftmost endpoint. Then the other thing we need to show is that we have continuity from the left at the rightmost endpoint. So I'm going to take my limit. X approaches 1 from the left of our function. Again, we can use that same work that we did over there on the right to show this. Okay, but it's going to become a direct substitution. So we have limit x approaches 1 from the left, 1 minus the square root of 1 minus x squared. And what's that going to give us if we do that work? It's going to be 1 also. And again, we just need to show that that's equal to the value of the function at that point, which it is, because if I plug in 1, it's going to give me that same thing. Okay, so now we've shown that our limit from the left at 1 is equal to the value of the function at 1. Therefore, this all down here tells us that this is continuous at our endpoints. Okay. And now we're done. Okay, so we showed that it was defined for all values in that interval. Then we showed that the limit existed and was equal to the value of the function for the open interval from -1 to 1. And then we also showed that it was continuous from the left and the right at those endpoints by showing that the value of the function was equal to what we got for the limit at both of those points. Okay. So those are kind of the 3 things you'd have to show if you want to prove that something is continuous on some closed interval now. So prove that it's defined, prove that the limit exists and is equal to the value of the function on the open interval, and then prove that it's continuous from the left and the right at your endpoints. Any questions on that one now? All right. Now, if f and g are continuous at some value a and c is a constant, then the following functions are also continuous at that a value. Okay, so the sum of 2 functions are going to be continuous if both of them are continuous at that value. The difference, f minus g, also going to be continuous at that value. A constant times a function will be continuous as long as it's continuous at that value. The product, f times g, will be continuous, and then f divided by g, assuming here that g of a is not equal to 0, right? Because we can't have 0 in the denominator. Okay, but that's our only restriction on that one. Okay, so if you know that 2 functions are continuous at the same value, the sum of those functions, difference of those functions, product, and quotient, as well as any constant times either one of those functions will all be continuous now. Now, the reason this is going to be useful is we know for sure that polynomial functions are continuous so far. We know that rational functions are continuous so far. And now we know that any sum of those types of functions, difference of those types of functions, product or quotient will also be continuous. Now, the theorem down here at the bottom says any polynomial is continuous everywhere. That means it's continuous on all real numbers from -infinity to infinity. And any rational function is continuous, right, wherever it's defined. So only on its domain, okay, but anywhere in the domain, it should be continuous. All right, now we want to find our limit as x approaches -2 for this rational function. All right, so how would we find the limit of this function now? Okay, do we need to factor the numerator this time? This time we can just direct substitute, right? Because it's not going to give us 0 in the denominator, so we don't need to simplify anything. We can just plug straight in. So that's all I have to do here. So we're going to get -2 to the third power plus 2 times -2 squared minus 1 all over 5 minus 3 times -2. So just remember, in this case, a rational function, we're allowed to direct substitute. And the reason we're allowed to direct substitute is because a rational function is continuous everywhere on its domain, meaning that the limit is going to be equal to the value of the function. Okay, so as long as -2 is in the domain, we can just plug straight in. Now we just need to simplify this. -2 to the third should give us -8. 2 times -2 squared. -2 squared becomes a +4 times 2 is +8. And we have our -1 over 5 minus 3 times -2, that becomes a +6, so 5 plus 6. And if we simplify that, what do we get? Yes, Rachel. Yeah, so I'm not going to ask you anywhere on the test to actually apply those limit laws. So if it's a place where you can direct substitute now, since we've covered the fact that you're allowed to do that, okay, you can actually do that now. Okay. All right, good. So if we direct substitute, that's going to give us -1 over 11. Yeah, so we cover those limit laws just to make sure it's clear why we're allowed to do some of the things we do. But then once we do that, then we can say, oh yeah, all polynomials, all rational functions. And in just a minute, you're going to see there's even more functions where we're allowed to direct substitute. Any questions on that one now? All right. So the following types of functions are continuous at every number in their domains. Okay, so we already talked about the fact that polynomials are continuous everywhere on their domain, which will be all real numbers. Rational functions are continuous on their domains. Root functions, so square roots, cube roots, fourth roots, whatever kind of root you want to use, those are all going to be continuous on their domains, right? So just keep in mind that it's only where they're actually defined. And then same thing for trig functions. Okay, they're going to be continuous everywhere on their domains. For sine and cosine, obviously that would be all real numbers because they're continuous everywhere. Just remember that some of your trig functions like tangent would have asymptotes, so they're only continuous wherever they are actually defined. Okay. Now, because they are continuous, that means that they're defined on that interval, the limit exists, and the limit is equal to the value of the function. Therefore, all of these types of functions now, if we're calculating a limit, we can direct substitute as long as it's in the domain of the function, right? So not only polynomials and rational functions now, but also any root functions and any trig functions, we're allowed to direct substitute to find our limits as long as that value is in the domain of the function. Any questions there? All right, so let's take a look at these. So we want to know, where are each of these continuous now? So the first one we've got is x to the 100th power minus 2 times x to the 37th power plus 75. So in what intervals would that function be continuous? Good, all real numbers, right? So there are no restrictions on the domain of that function. It is a polynomial, and so it's going to be continuous everywhere. from negative infinity to positive infinity. Any questions on that one? All right, so now we have a rational function, x squared plus 2x plus 17 over x squared minus 1. Where would this one be continuous? How would we find that? Okay, good. So we know the denominator can't be equal to 0, and then we're going to have to factor to find those restrictions, right? Because that's going to tell us where we have discontinuities, and then we know it should be continuous everywhere on its domain. So we're going to say x squared minus 1 can't be equal to 0. If we factor that, what are those factors going to be? Good. X minus 1 and x plus 1. And then setting each of those factors not equal to 0. Tells us that x cannot be equal to positive 1 and x cannot be equal to negative 1. So those are the restrictions on the domain. That means that's where we're going to have discontinuities on our graph. So what would be the intervals where this function is continuous then? Good. So negative infinity to negative 1. And we have our union. We have to go from negative 1 to positive 1, another union, and then from 1 to infinity. Okay, so it's going to be continuous everywhere on its domain, and the only place where it's not defined is at negative 1 and positive 1. Any questions on that one? All right, and then h of x here. This time we have the sum and difference of multiple functions, but they're all root functions or rational functions, right? So we know now that it should be continuous on its domain because it's just the addition and subtraction, right? Sum and difference of some of the functions that we know are continuous. How would we find where this is continuous then? All right, good. So we need to find the discontinuities of each of our terms here, right, or each of the function pieces. So if we look at the first part, the square root of x, what do we know about the square root of x? Okay, good. Its domain is from 0 to infinity, right, because it has to be positive or 0. We can't have any negatives in there. So we know that x has to be greater than or equal to 0. Right, that's one restriction we have on our domain. That's also going to tell us one of our restrictions on continuity. All right, now let's look at the second piece here, x plus 1 over x minus 1. Where is that going to have a discontinuity? At 1, good, right? Because we would say that the denominator x minus 1 can't be equal to 0. That tells us that x cannot be equal to 1, so we have a discontinuity at 1 now. Right, what about the last one, x plus 1 over x squared plus 1? So where would that have discontinuity? All right. So plus or minus square root of -1 is an accurate statement, right? Because you would take x squared plus 1 can't be equal to 0. In this case, we can't factor, so we could move the 1 over. That would give us that. And then that's going to give us x can't be equal to plus or minus the square root of -1. What's the square root of -1? Okay, I, right? So this is just x can't be equal to plus or minus I. But remember, for our domains now, if we're graphing, we're only talking about real numbers. So do we have any additional restrictions on our domain or any discontinuities based off of what we just got there? No, right? So if you get imaginary results, you can just ignore them, okay, because that's going to have no impact on the actual graph or where it's continuous. So the only restrictions we have now are that x must be greater than or equal to 0 and that x cannot be equal to 1. So what is the continuity going to look like? What intervals will this be continuous? Okay, good. So we're including 0 here, so bracket on that, up to 1, parentheses, because we don't want to include the 1, and then we're going to go from 1 to infinity. So that's where this function is going to be continuous this time. If you think about it, right, x squared we know is always going to be positive or at least 0. And if we add 1, that's going to be a positive value. So you're never going to be able to get a 0 in that denominator, x squared plus 1. That's why that function is actually defined for all real numbers. So it's really only the other two pieces we have to worry about for continuity now. Any questions on that one? All right. And now we want to find the limit as x approaches pi of sine of x over 2 plus cosine x. All right, so how are we going to find that limit? We can do direct substitution, right? So in this case, remember, we know that trig functions are continuous. So that means sine of x and 2 plus cosine of x are continuous. And we know that the quotient of two continuous functions should also be continuous. So now this function that's given should be continuous on its domain. So as long as pi is in the domain of our functions, then we can direct substitute. Well, pi is in the domain of sine of x, pi is in the domain of 2 plus cosine x. So we can direct substitute as long as we don't get 0 in the denominator, right? That's the one stipulation. Okay, but in this case, 2 plus cosine of x should be good. So we're just going to take sine of pi divided by 2 plus cosine of pi. And now we're just going to simplify. Okay, so what's the sine of pi? Zero. Good. So sine at pi should be 0. Then we have 2 plus. What's the cosine pi? Okay, cosine at pi should be a -1. Simplifying that just gives us 0 over 1, which is equal to what? 0, right? So we now know now that the limit as x approaches pi for that function should just give us 0. Again, the reason we're allowed to direct substitute is because both of those trig functions are continuous on their domains. Therefore, the quotient is also continuous on its domain, and we can direct substitute as long as pi is in the domain of that function, or both of those functions. Any questions on that one now? All right. Now, if f is continuous at b, and the limit as x approaches a of g of x is equal to b, then the limit as x approaches a of the composite function f of g of x is equal to f of b. Okay? So it says, in other words, our limit as x approaches a of f of g of x is just f of the limit of g of x as x approaches a. Okay? So we're basically taking our limit as x approaches a of the inside function and then evaluating that at that value for f, right? So substituting that limit value in for the f function now. Now this is all assuming, right, that f is continuous and that the limit actually exists for g of x at that value, right? So both of those things have to be true to be able to do this. Now, the second part down here says that if g is continuous at a, and if f is continuous at g of a, then the composite function f of g is continuous at a. Now, we've shown already, right, that the sum of two functions, difference of two functions, product, and quotient, all of those will be continuous as long as the original functions were continuous. Now we're saying, well, what if you have a composite function, right? One function within another function. It's not that just both functions have to be continuous. They have to be continuous at specific places now, since we're substituting one into the other. Okay, so that's what we're really saying in this case. Okay, but in general, if you have a composite function of multiple continuous functions within those domains, now we know that the overall composite function should be continuous. All right, so now we want to know where are each of these functions going to be continuous. Now, what we're going to have to show here is that first we can actually rewrite this as a composite of multiple functions. So we need to break this down into their composite pieces, and then if we can show that each of those is continuous, we know the overall function should be continuous on its domain also. Okay? So how could we break down the sine of x squared? What functions could we compose to give us that? All right, good. So we can use sine of x and x squared. So I'm going to say f of x equals and g of x equals. I'm going to let g of x be the inside function this time. So that's going to be x squared, which means our f of x is just going to be sine of x. And so that's just equal to f of g of x now. Right, now we ask ourselves, are both of these functions continuous on their domains? Yes, right? X squared is polynomial. It's continuous on its domain, which is all real numbers. Sine of x is a trig function. It's also continuous on its domain, which in this case is all real numbers. So now, where is sine of x squared going to be continuous? All reals. Good. Right? Since there are no restrictions in this case on either one of those pieces, we can just say that the continuity here is from negative infinity all the way to positive infinity. And you might be saying, oh, well, that's obvious. That's fine, right? Okay, but again, we have to show here that we can rewrite it as the composite of multiple functions first to prove then that it is actually continuous on its domain. And that's what we've shown here. Any questions on that one? All right, let's look at the next one. So same thing, we need to break it down into its composite pieces first to show that it's actually going to be continuous on its domain, and then we can find where it's continuous. How could we start this one? All right, so we actually don't need to do any simplifying, multiplying by conjugate, anything like that. We just need to break it down into the composite pieces just like we did with part A. So what function could I start with here if we're going to break it into its pieces? Okay, so 1 over x, right, would be one function. That's actually going to be the final function that we apply, so that'll be our f of x. Okay, what would another piece be? All right, so we need some kind of square root for sure. We need a -4 for sure. Whether you separate those into two separate functions or not really doesn't matter too much here. I'm going to do it as two separate steps. I'm going to let f of g, so we got fg, I'll call this one h. Okay, so I'm going to do the x minus 4 as that step and the square root of x as that step. And so what would the last function have to be here if we were to substitute in now to give us what we want? Good. So just what's inside the square root. So x squared plus 7. Okay, so basically I'm substituting the x squared plus 7 into the square root. Then I'm taking that and I'm subtracting 4. And then I'm taking that and I'm putting it in the denominator. Right. So that's what this would give us now. All right. Now, looking at what we've got here, are all 4 of these composite pieces of the composite function continuous on their domains? Okay, so which one do you think is not continuous on its domain? Okay, so 1 over x is what type of function? It's rational, right? Are rational functions continuous on their domains? Yes, right? Okay, so we're saying that it's defined everywhere, right? We're just saying that on the domain of that function, it is continuous, right? So this one definitely is going to have a discontinuity at 0, right? But for its domain, it's going to be continuous, right? Same thing with x minus 4. It's polynomial. It's going to be continuous everywhere on its domain. Yes, the domain happens to be all real numbers, okay, but all we're saying is that it has to be continuous on the domain of the function. Is the square root of x continuous on the domain of that function? So square root of x. Is it continuous on the domain? It is, right? So even though, again, the domain here is just going to be from 0 to infinity, we know that it's continuous on that domain. And then the last one, polynomial again, x squared plus 7, also going to be continuous on its domain. So we've broken this thing down now into some composite of polynomial functions, root functions, and rational functions, which we know now means that the original function should be continuous on its domain. Any questions on that? So now we just need to find the domain of the original function, and we know it'll be continuous there. So how are we going to find that? Okay, good, right? Set the denominator not equal to 0 here. So we have square root x squared plus 7 minus 4 cannot be equal to 0. How are we going to solve that now? Okay, good. We move the 4 over, so that's going to give us square root x squared plus 7 cannot be equal to positive 4. And then we can do what? Good. Square both sides to get rid of that square root. So x squared plus 7 cannot be equal to 16. What's our next step? Good. Move your 7. So x squared cannot be equal to 9. And then we can do what? Take the square root. So x cannot be equal to what? Okay, just 3. Plus or minus, right? So don't forget your plus or minus here. So x can't be 3 or negative 3. So that tells us where we have restrictions on the domain, which means we're also going to have discontinuities there. So where is this function going to be continuous? Okay, so remember, it's not defined at 3 and negative 3, right? So we definitely cannot include those values, okay, but it should be continuous everywhere else. So from negative infinity all the way to negative 3, from negative 3 to positive 3, and from positive 3 all the way to infinity. So remember, the work over to the left is just showing that this is a composite of multiple functions that we know are continuous. And as long as we show that, then we can just find the domain of the first function that we started with, and that'll tell us where we have continuity. Any questions on that one now? All right. Now, intermediate value theorems. This is the last thing we're going to cover here in this section. Okay, so suppose that f is continuous on a closed interval from a to b. We're going to let n be any number between f of a and f of b where they're not equal to each other. So f of a can't be equal to f of b. Then there exists a number c in the interval from a to b such that f of c is equal to n. Okay? Now, the graph here helps a lot in visualizing what we're doing. So we have an interval, closed interval from a to b. So here's a, here's b. Those are our x values. Then we have two y values, f of a and f of b, where they cannot be equal to each other. Right? So here's my f of a, here's my f of b, not equal to each other. In that interval now from a to b, there's going to be some value c, right? We don't know exactly where it is, but somewhere in between a and b, there's going to be some x value, which we're going to call c, where the corresponding y value is equal to this n value that's between f of a and f of b. Now, we're not saying that that's the only place that it happens, right? Because the other graph shows us that we could have in this same interval multiple points where we hit that same n value, right? So in this case, 3 different places where that happens. And we know it happens at least once, because if the function is continuous, it's going to hit every single y value between f of a and f of b at least one time. That's all the intermediate value theorem tells us. If it's continuous on an interval, then it's going to hit every y value between your starting point and your ending point somewhere in that interval at least one time. Okay? Any questions on that? Again, key word here, function has to be continuous, right? Because if you have discontinuity there, we cannot guarantee that you're going to hit every single value in between, okay? All right, So last example, we're going to show that there's a root of the equation between 1 and 2. All right, so let's think about what this is asking us to do now. What does it mean for something to be a root of an equation? Okay, good, right? A root is just an x-intercept where it crosses the x-axis, right? Another name for that would be a 0. So we're just trying to show now that there is an x-intercept for the graph of that equation somewhere between 1 and 2. Well, I'm just going to sketch this real quick just to kind of give us an idea of what we're trying to show then. So if this is 1, this is 2. We want to show that somewhere between there, right, and I don't know exactly where, we want to show that this graph crosses the x-axis. Now, thinking about intermediate value theorem, what we just looked at, how could we show that? How could we prove that there's actually an x-intercept somewhere on that interval? Perfect, right? If I substitute in the values 1 and 2 into my equation, as long as one of them is negative and one of them is positive, I know a polynomial is continuous. Therefore, it's going to have to pass through the x-axis to get from the negatives to the positives, right? So if I can show that one is negative, one is positive, then I know there has to be a 0 or a root somewhere in between those two values. That's what we're going to do next. We're just going to plug in the 1. So 4 times 1 cubed minus 6 times 1 squared plus 3 times 1 minus 2. So if we simplify all of that, what's that going to give us? Should be negative 1. Good. So we have 4 minus 6 is negative 2, plus 3 is 1, minus 2 should be negative 1. Okay, so we get a negative value, right? So this one is less than 0. So I know that this point, right, is going to be somewhere down here now. Now we're going to substitute in the other endpoint. So 4 times 2 cubed minus 6 times 2 squared plus 3 times 2 minus 2. Okay, so if we do that, what is that going to give us? Okay, so I got 12. Let me double check. So 2 to the third is 8 times 4 should be 32. Minus 6 times 4 is 24. Plus 6 minus 2. Okay, good, right? So that should give us 8 plus 6 is 14 minus 2. This should give us 12. All right, and so 12 now is a positive value that is greater than 0. It's going to be way up here somewhere, right? But all we care about in this case is that 1 is negative, 1 is positive, and this function is a continuous function, right? Because that is key. If you don't have a continuous function, this doesn't work. But that tells us then that somewhere in between here, as it passes from that point to that point, it has to cross over the x-axis. So we do indeed have a root there. Okay. And that's all you would really need to show for a problem like that, right? Just tell me that it's continuous, right? Because that's important. And then show that one endpoint is negative, one endpoint gives us a positive. And if that's the case, then we know somewhere in between there it has to cross over the x-axis. There has to be a root. Any questions on that one now? All right, let's go ahead and take our break. Okay, so we'll take 5 minutes here, and then we'll go through the practice test when we come back. So 10:55, we'll get started back up, and we'll go through the practice test. All right. So let's just start here with number one on the practice test. Again, you can find this in the practice test section on Blackboard if you want to download it and work through it. I think the best way to prepare for one of my tests is to actually take that test and actually just work through the problems, right? And then use my solutions to check yourself. But just looking over the solutions is probably not going to help as much as actually working through the problems, right? So just do that, check yourself. And then if there are particular ones where you're still struggling or need more practice, let me know. And I'll be happy to find you some more practice problems similar to those types of problems, okay? All right, so let's look at number one. F of x equals 4 plus 3x minus x squared. We want to evaluate the difference quotient, and I give you the formula for that, right? So it's f of a plus h minus f of a all divided by h. All right, so if we start here with our formula, f of a plus h, what's that going to give us if we just find that first part? All right, so that's going to be the second part, right? So when I substitute in the a value, for the f of a plus h, remember we got to plug in the actual a plus h everywhere we see an x. So we're going to start with 4 plus 3 times a plus h minus a plus h squared. Then we're subtracting f of a, which is going to be what Rachel's got right there. So that's 4 plus 3a minus a squared. All of that now goes over h. Okay? That's fine. All right, so just make sure in this case, right, start with f of a plus h, plug that in everywhere you see an x, and then we're subtracting the entire f of a function. Okay, so just make sure that all of that is grouped together now. Any questions just on the setup for that one? All right, now let's simplify. Okay, so what's the first thing we can do here? All right, let's expand out the a plus h squared. I'm going to go ahead and distribute this 3 also, so we'll get 3a plus 3h. And if we expand out a plus h squared, what's that going to give us? Good. A squared plus 2ah plus h squared. So remember, that's just a plus h times a plus h. If you need to show the work for that over to the side just to make sure you got it, that's fine. Okay, just make sure you're using FOIL there and combining like terms. I'm also going to go ahead and distribute out my negative down here now. So that's going to give us minus 4 minus 3a and plus a squared all over h. Now, the only other thing we can do before we start combining like terms, we have this negative in front of the what we expanded here, so let's distribute that out. Now we've got 4 plus 3a plus 3h minus a squared minus 2ah minus h squared, and then just bring everything else down. Good. Now we can combine like terms. So if we do that, what are we going to get? Good, right? So we're left here. The 4's cancel out. The 3a minus 3a cancels out. And the negative a squared and positive a squared cancels out. So that leaves us with 3h minus 2ah minus h squared all over h. Right. Then what can we do at that point? Good. Factor out your h in the numerator. If we do that, we get 3 minus 2a minus h all over h. And now if we simplify that, what's that going to give us? Good. So the h's cancel here. We're left with 3 minus 2a minus h. So that is our final. Okay. Any questions on that one now? And again, that formula there is going to be really important as we go into chapter 2. Right? So that's why I start with this one on the test. I want to make sure that you know how to actually use that formula and actually simplify it. Okay. All right. Number 2. So now we're just describing how the graphs of the following functions can be obtained from the graph of f. Okay. So we're basically saying what types of transformations are being applied in this case. All you have to do is just list out the transformations. So for the first one here, what's one transformation that we're going to have? Okay, good. So we're going to shift to the left 3 units. Remember the plus 3 grouped in parentheses there gives us a shift to the left. And then what else? Good. Shift down 4 units. So the minus 4 on the outside is going to shift the graph down 4 units. And that's all there is for this one, right? So just make sure, though, review all of your different types of transformations because any of them could show up, right? Your reflections, your stretches and shrinks, your shifts up and down, left and right. So just make sure you know what all of those different ones would look like here. Any questions on that one? All right, let's look at B. So what transformations are we going to have this time? All right, we're going to reflect. Across the x-axis. Good. So remember, a negative in front of the function is going to give us that reflection over the x. We're also going to have a shift up 1 unit. Right. So let me get that one in there. Shift up 1 unit. And then we have the 2 on the inside. Okay, and so that is going to give us something horizontal because it's grouped with the x. And in this case, because that value is bigger than 1 and we're multiplying, it's going to give us a horizontal shrink by that factor. Okay, so horizontal shrink. By a factor of 2. Okay. Or if you put 1/2 there, that's fine also, because really that's what's happening, right, is the entire graph is shrunk in half horizontally now. Any questions about those transformations? Okay, and real quick before we move on, what if that 2 was on the outside in front of f of x? What would that do instead? The 2 is multiplied. That would be a vertical stretch. Good. So remember, on the outside in front of the f would be vertical. Bigger than 1 would make it a stretch. So we'd have a vertical stretch if the 2 was on the outside. What if the negative was inside the parentheses with the x? What would happen? Good, right? The reflection would be over the y-axis instead if that negative happens to be on the inside. Okay, so just keep in mind, again, just review all those different rules for your transformations and make sure you know what each one of them looks like. Any questions on the transformations now? right. Number 3. Okay, so now we want to figure out, is each of these functions even, odd, or neither? So how are we going to determine if we have an even function, odd function, or neither? Good. A negative x and see what happens. So we're going to do f of negative x. For the first one here, that's 1 plus 3 times negative x squared minus negative x to the 4th. All right, so now if we simplify this, what's it going to give us? Good. It's going to be the same as the original function here, because we're going to have 1 plus 3 times negative x squared becomes a positive, because we're raising it to an even power. Then we have our minus, same thing with negative x to the 4th. That's going to become positive, because we're raising it to an even power. And now looking at that, that's the exact same function we started with. So what can we say about this function now? Good. This one is going to be an even function. So that's the work I would want to see, right? Actually substitute in the negative x, simplify it, see if you get the same function. Opposite of the function would mean it's odd, and if you get neither of those things, then it's neither. All right, so let's look at b. Same thing, we're going to do f of negative x. When you say is b just one whole term, so we usually only use the word term with polynomials, right? Meaning that you would have like a coefficient, a variable, and a power. So we have to think of this as a rational function, right? So even though it has a numerator, it has a denominator, we wouldn't say that it has multiple terms necessarily. We would just say that overall it is a rational function now, okay? All right, so we're going to have negative x over negative x squared plus 1. So now if we simplify that, what are we going to get? Good. So we have a negative x in the numerator. The negative x squared in the denominator becomes positive x squared, and then we have our plus 1. So first off, is that the same function we started with? No, right? So it's definitely not an even function. Is it the opposite of the function we started with? So I'm getting some yeses and some no's here, right? It is actually the opposite of the function we started with, right? And let's think about why. If I had the fraction 1/2, what's the opposite of 1/2? Negative 1/2, right? So in that case, I only need one of those values to become a negative, not both, right? Because if both of them became negative, the negatives would cancel out and it would become a positive anyway, right? So in this case, I only need the numerator to be a negative, denominator stays the same, and so this is actually the opposite of what we started with. So now we can say that this is actually an odd function this time. Okay, so be really careful with those fractions, right? Just making the numerator or just the denominator a negative and keeping the other one the same actually makes it the opposite. Any questions on that one? All right, let's look at part C. Same thing, we're going to do f of negative x. This time we're going to have negative x times the absolute value of negative x. Now, if we simplify that, what's that going to give us? Okay, so yeah, negative x times the absolute value of negative x, right? Is there anything we could say, though, about like the absolute value of negative x? Okay, it's going to become positive, right? So we know that this is equal to just negative x times the absolute value of x. Because that negative inside the absolute value bar makes no difference, right? It's just going to be the same as the absolute value of x anyway. Now, looking at what we've got here, is it the same as what we started with? No. Is it the opposite of the function that we started with? It is, right? So this time, negative x times the absolute value of x is exactly the opposite of the function we started with. So again, we can say that this one is an odd function. Any questions on that one now? All right. Number 4, intermediate value theorem. A neither would just mean that you don't get either the same function you started with or the opposite. So just to kind of give you an example, let's say you had a polynomial like x squared plus x minus 5, right? When I substitute in a negative x into that function, you would get negative x squared plus negative x minus 5. Squaring the negative x would give us x squared, then plus a negative x, same thing as minus x, and minus 5. So again, not the same as the function we started with, but also not all the signs switch, so it's not the opposite of the function we started with. So this one right here would be a neither. Okay. And that's just one example, right? Because there's several, other types of functions you could use there. Okay, but again, if it's not the same function and it's not the opposite of the function, then we know it's neither. Good there, Hiro? All right. Any other questions there? All right. Number 4. So intermediate value theorems, this is what we just looked at in the notes. We want to show that there's a root of the equation on the interval from 0 to 1. All right. So how are we going to show that there has to be a root in that interval now? Good. Plug in the 0, plug in the 1, okay, because we do have a continuous function this time. Cosine is continuous on its domain, which is all real numbers. X is polynomial. It's continuous. This is the difference of two continuous functions. So we know that this is a continuous function. So now we can just plug in the 0 and the 1. So we're going to find f of 0 and f of 1. So we plug in 0 here. That's going to give us cosine of 0 minus 0. What's the cosine of 0? If it's not continuous, we can't apply intermediate value theorem at all, right? So if I ask you to use the intermediate value theorem, assume it's continuous, right? But write out that it is, just so I understand that you recognize that it has to be. But I would never give you a discontinuous function and ask you to use intermediate value theorem, okay? All right, so cosine 0 is going to be 1, good, minus 0, and so that's equal to 1. All right. Now, again, all we're trying to prove here is that one of these values is positive and one of them is negative, because then we know that it has to pass through 0 at some point. So that one is our positive. That's our greater than 0. Then we're going to do cosine of 1 minus 1. Now, cosine of 1 is not a nice value, right? You'll have to use your calculator for this. Make sure you're in radian mode again if you haven't switched over to radian mode already. And so what's cosine of 1 minus 1 going to give us? Okay. So I'm getting a different decimal from that. Anybody else getting a different value? Yeah, I did. I recognize that now because I'm looking at my answer key. So yeah, so I got the wrong decimal. Okay, but it's not going to affect the overall answer here. So did you get the decimal there, Dean? Okay, good. Yeah, so negative 0.4597, right? If you wanted to keep more decimal places, or negative 0.46 is fine. Okay, because all we're trying to show here is that we get something that's less than zero. That is a negative value. That is less than zero. Right. All right, Hyro, do you see how we got that decimal now? Just want to make sure that you're able to get that negative value. Good. Okay. Any questions about how we got that now? And then at this point, right, we know that putting those two things together, right, one's positive, one's negative. Therefore, there's a root in the interval from 0 to 1, right? Because it has to cross over. It has to pass through 0 somewhere in that interval now. Okay, so yeah, again, if you're looking at my answer key, I accidentally had my calculator in the wrong mode. That's how I got the value that I've got there. Okay? But in either case, right, it does come out negative. And so we know that there's going to be a root there. Any questions there now? All right. Number 5. Okay, so this time you're given the graph and you're asked to find each of these limits. So the first one we're looking for is the limit as x approaches 2 from the right of f of x. And this is a little tricky to look at. Okay, so just make sure this is our y-axis, this is our x-axis, right? So right there in the middle, 0. Okay, so if we're looking at 2 from the right, so we're coming in, here's 2 from the right-hand side. And so it looks like we're approaching a value of 3, right? Because here's 1, 2, this would be 3 right here. So this is equal to 3 now. Any questions about how we got that value? All right, so the next one, we're looking for the limit as x approaches negative 3 from the right. Good, right? So negative 3 would be right here. We're approaching from the right, which is going to be this piece of our graph. And in this case, we are approaching a value of 0 from the right-hand side. Any questions on that one now? All right, next one we're looking for is limit as x approaches negative 3 overall. Good. Why is this one going to be a does not exist? Good, right? So the left and the right-hand side approach different values, right? Because from the left-hand side, we're approaching this value down here. From the right-hand side, we know we're approaching 0. So this does not exist. And the directions up here says find each limit or explain why it does not exist. So our explanation here would be that the limit as x approaches negative 3 from the right is not equal to the limit as x approaches negative 3 from the left. Okay. And that's all the justification I would need to see there. is that the left-hand and right-hand limits are not the same. Questions on part C now. All right, part D. Now we want to find the limit as x approaches 4. Scroll back so you can see the graph. So what's our limit as x approaches 4 going to be? Good, should be 2, right? Because here's 4 on our graph. As we approach from the left and the right, we're approaching where that open circle is, right? So even though the function's defined somewhere else, it's only the value that we're getting close to on either side. So that should be a value of 2 now. All right, and then part E, we're looking for the limit as x approaches 0. So what's that limit going to be? Okay, good. So it's going to positive infinity on both sides here. So we can say that that limit is infinity. Okay. Or again, if you put that it does not exist, that's also accurate, right? So either one of those answers would be acceptable there. And if you said it does not exist, though, I would need the justification to be that it's going to infinity, right? Any questions on that one now? All right. Number 6. Okay, so now we're going to calculate each of these limits algebraically. So we want to find the limit as x approaches -3 of that rational function. All right, so how are we going to do this? Okay, good. So we can't direct substitute because it gives us 0 in the denominator. So we are going to have to factor this time, see if we can simplify it. So we're taking limit, x approaches -3. How's the numerator going to factor? Good. We can factor out the x. So x times x plus 3. And then what are the factors going to be in our denominator? Good. We're going to have an x plus 3. Oops, and an x minus 4. All right, so now when we simplify that, we do have a common factor that cancels out. So now we have the limit as x approaches -3, x over x minus 4. And then what can we do at that point? Now we can direct substitute. Good. So when we do that, we get a -3 up top, -3 minus 4 in the denominator. And so when we simplify that, what's that going to give us? Good. All right, so -3 over -7, but a negative over a negative becomes positive. And so our limit is just 3/7. Any questions about finding that limit? Okay. And that is how I want to see this one worked out. So I don't want to see a table of values where you're approaching -3 on either side or anything like that. Actually show me the algebraic way of getting to that limit now. All right, let's look at B. So what can we do with B now? Good. We're going to have to expand this time because, again, we can't plug in the 0 because that would give us 0 in the denominator. So if we expand the numerator here, what's that going to give us? Okay, sorry, you already got it there, Dean. Thank you. 25 minus 10h, and then plus h squared. And then I'm going to bring over my minus 25. It's over h. All right, now if we combine like terms in our numerator, what are we going to get there now? Good, right? So the 25 minus 25, that's going to cancel out. So we're left with negative 10h plus h squared. And then what can we do from there? Good. Now we can factor out an h in the numerator. So limit h approaches 0, h times negative 10 plus h all over h. All right, what's the next step? Good. Cancel out your factor of h in the numerator and denominator. Come down here, so limit h approaches 0, negative 10 plus h. And at that point, we can do what? Good. Now we can direct substitute, which is going to give us what then? Just negative 10. Good. Negative 10 plus 0, which is negative 10. Any questions on that limit? All right, part C. So now we've got the limit as u approaches 2 of this algebraic function here, because we have a square root in the numerator. So what are we going to have to do to calculate this limit? Good. This is the example where we have to use the conjugate, right? We can't just plug in the 2 because that would give us 0 in the denominator. So we're going to multiply numerator and denominator by the conjugate. Remember, the conjugate here is just exactly what we have in the numerator, except there's going to be a plus instead of a minus. So we have the square root of 4u plus 1 plus 3. And then we have to multiply the denominator by exactly the same thing. Okay. Now, when we multiply the numerator, remember that's going to be FOIL. And so what's that going to give us if we multiply the numerator now? Anybody else got a black screen? Yours too? All right, give me just a second. See if I can fix it. Okay. Is it back now? Good. Perfect. All right. Yep. All right, so now if we multiply the numerators here, what's that going to give us then? Good, right? So the square roots here cancel and leave us with 4u plus 1. The last terms, -3 and +3, is going to be a -9. And then remember, the outer and inner terms cancel, right? So we don't even have to worry about those. And then our denominator, I'm going to leave factored, right? So we have our u minus 2. And then we have the square root of 4u plus 1 plus 3. Any questions up to that point? All right, so if we combine like terms in our numerator now, what's that going to give us? Good, so +1 minus 9 is a -8, so we have 4u minus 8. I'm going to keep my u minus 2, square root of 4u plus 1, plus the 3 out here. All right, now what can we do at that point? Okay, good. So in the numerator here, what's our common factor? Okay, do we have anything bigger than 2? 4, right? So 4 is actually the common factor up there, so we can actually factor that out. So limit u approaches 2. We have 4 times u minus 2. And then down here we have u minus 2 times the square root of 4u plus 1 plus the 3. Okay. Now what can we do? Good. We have a common factor of u minus 2 in the numerator and denominator. Those are going to cancel out. So now we have the limit as u approaches 2, 4 over the square root of 4u plus 1 plus 3. Now we can substitute. Good, because we're not going to get 0 in the denominator anymore. So that's going to give us 4 over square root 4 times 2 plus 1 plus the 3. And if we simplify that now, what's that going to give us? Good, 2/3, right? So just to kind of put an intermediate step in there, this is going to give us 4 over 3 plus 3, right? Because that's going to have the square root of 9 under the radical. Square root of 9 is 3, so that's where we get the 3 plus 3. 4 over 6, though, is going to simplify to 2 over 3. So 2/3 is our limit now. Any questions on that one? All right. Last one, number 7. Okay, so this time we're given a piecewise function. We're asked to find each one of these limits now. So if we're looking for the limit as x approaches 0 from the right of that function, how are we going to do that? Good. Since we're approaching 0 from the right, we've got to figure out which piece of the piecewise we're looking at. Well, 0 from the right would fall within this piece of our domain, right, between 0 and 3. So now we can just direct substitute. We have to make sure we're substituting into the 3 minus x. That's going to be 3 minus 0. And so what's that limit going to be? Just 3. Good. So we're allowed to do direct substitution here. The key, though, is figuring out which piece are we looking at and making sure you're plugging into the right place. Any questions on that limit? All right, let's look at part B. Now we're looking at the limit as x approaches 0 from the left of that function. How are we going to find that? Good. This time, as we approach 0 from the left, that means that x is less than 0. So now we're substituting into the square root of negative x. So we're going to have the square root of negative 0. But what is the square root of negative 0 going to give us? Just 0, right? Any questions on that limit? Okay, now C is asking for the overall limit as x approaches 0. Good. In this case, this does not exist. And I don't ask for a justification here. I assume in this point you would know it's because the 3 and the 0 are not the same. So if the limit from the left and the right are not the same, that's how we get does not exist there. Any questions on that one? All right. So now part D, we're looking for the limit as x approaches 3 from the right. So where are we going to substitute this time? Good. The last piece, x is greater than 3. We're coming in from the right, so that's where we want to be. So this is going to be 3 minus 3 squared, which would give us what? Just 0, right? So 0 squared is 0. Right, now we want to look at our limit as x approaches 3 from the left. So where is that going? Good. The middle piece, 3 minus x. So we're going to have 3 minus 3. In this case, that gives us what? 0. Now if we look down here, the limit as x approaches 3 is going to be what? 0 also, because as long as the limit from the left and the right are the same, we know the overall limit is going to be that same value now. Any questions on D through F? All right. That's the test, right? So like I said, the actual test will be very similar, same number of questions, same types of questions, obviously different numbers and things. But if you can do the practice test without looking over my solutions, right, then you should be prepared to actually sit down and take the test. So like I said, I would go through the practice test, practice those problems, make sure you know how to do it. Do review some similar types of problems, right, just to make sure you know all the little, like the even and odd stuff especially, and then the transformations, make sure you know all of them, that kind of thing. But in general, right, it's going to be laid out very similarly, okay? Any questions about anything on here now? All right, so like I said, I'll be around through the afternoon and tomorrow. So if you have questions, feel free to email me. Send me questions about homework through WebAssign if you have them, right? I'll be happy to respond to those. Okay, Dean, I can get to your question in just a minute about the homework. Don't forget, homework 1.5 to 1.8 is due by midnight tomorrow night now, so you've got an extra day to get that one done. But the test is also due by midnight tomorrow night, so just make sure you've prepared some time to do both of those things. I think that's all. Let me know if you got questions. Have a great long weekend because it is Memorial Day weekend, so we will not meet on Monday. Don't forget that. So I will see you all again on Tuesday.